Wasabi, you guys. Welcome to Integration Bee Training for Advanced. This is part 17.4. So we're still into the Laplace transform training. In this section, we'll be learning some special Laplace formulas. So this is just mainly just pure Laplace transform formulas to know. Okay? So let me go ahead and list them. So we have the special types of Laplace transforms. The Laplace for this one, we have the Laplace of 1 over square root of t. Okay? The Laplace of this function is equal to the square root of pi over s. Okay? So, I mean, another way to think about it is to prove this. I think it's just mainly a Gaussian integral, right? If we have e to the negative s t, and we have dt over square root of t, right? You could perform a u substitution where this becomes from 0 to infinity. This becomes 2 when you substitute the square root, right? We get 2e to the negative s u square, and this is definitely a Gaussian integral, which does turn out to be the square root of pi over s, right? The s from the Gaussian integral, and then the 2 helps cancel out the root pi over 2. Okay, so that's where this comes from. All right. I guess I'll leave it right there for now. The Laplace of the square root of t is equal to the square root of pi over 2. And this time it's s to the power of negative 3/2. We're not really going to use this too often, but just to be safe, it will quite show up. And the procedure is the same way. It's the Gaussian integral. It comes from the Gaussian integral. Okay. Now we've seen this before, but I'm going to apply it here. Right? We have sine of t over t. We've seen this so many times if you remember from the previous video where we learned the integration property of the Laplace transform. Here, it's actually very important that you do memorize this because this is just simply inverse tangent of 1 over s. It is not inverse tangent of s, it is inverse tangent of 1 over s, meaning that this Laplace is equal to inverse cotangent of s. Okay? So be very careful. Be extremely careful. Okay? Okay, next, we have our last one, our last special. This one's very hard to kind of memorize or detect, but I'll try my best to help you out with that. So we do have a very special Laplace transform here, and it is e to the t minus 1 over t. Okay. There's a reason why I didn't show this in the previous, because it was a little difficult. It was just kind of obscure. Anyways, I liked this because the answer is actually very nice. It's ln of s over s minus 1. And of course, as you can see, if we plug in infinity, it will just be ln of 1, which equals to 0. So it's also a very nice identity here. And to help you memorize, it is just like the integration property, right? From 0, and we have e to the negative st, and we have e to the t minus 1 over t dt, right? Using the Laplace, the integration identity, this is just simply s over infinity, and then the Laplace of e to the t is pretty much what, 1 over x minus 1 minus 1 over x. I think I did that correctly. I think I did that correctly. Yeah. And so now this is just simply ln of s over s minus 1. Yeah, because the infinity goes first and then s. So yeah, this seems to be right. Okay. All right. Now that we have these formulas in the back of our mind, let's go ahead and apply these special Laplace formulas. Oh God. Okay. Don't freak out. Do not freak out. Breathe. And let's just kind of simplify this a lot further. We notice that square root of x is just to freak us out, but it's going to cancel out with this. So just by seeing that, we can see that this is just a Laplace of sine of x plus 1 over square root of x, with s equaling a half. So now this is just simply what the Laplace of this is 1 over 1 plus s squared plus, and then the square root of pi over s. Okay, with s equal to half. So now this answer is just simply what, if we plug in a half here, that's like 1/4. So it's going to be like 4/5. 4/5 plus, and then a half here, it's just the square root of 2 pi. So this is our answer. Okay, very straightforward. See, it wasn't that bad. It looked ugly. It was definitely an ugly integral, but with the power of the Laplace transform, this is simple. It's very easy and very quick to integrate. Oh God! Again, don't freak out. I think this is just to stall us. So let's not get distracted. So if we compute this, we simplify. This is what dx over x over e to the x, and this is just simply 1 minus 1 over e to the x, right? So I see that we're going to get something like, search infinity. Let's see, well, this is technically e to the x minus 1. So we have what? X e to the 3/2 x, and then e to the x minus 1. Pretty much, yeah. Okay. Huh. What now? You're probably thinking, oh, let's just split it. Okay, that's the easy way route, but we have a faster way. And of course, the faster way is using the special Laplace transform formula. This is simply the same thing as this. Aha, don't forget about this. So this is s equal to 3/2, right? Now this is simply ln of s over s minus 1 with s equal to 3/2. So now this is equal to the ln of 3/2 divided by 3/2 minus 1. That's 1/2. So the answer is ln of 3. Ooh, a very nice integral here. I bet you can already see what to do immediately, right? Yes, this is simply a Laplace transform of 1 over the square root of x. Yes, this is where s is equal to, this is 1/4. And so now we have the square root of pi over s, where s is equal to 1/4. And so now what we have is this integral is simply equal to 2 times the square root of pi. Okay? Look how fast that was. We literally just saw that in less than like, what, 30 seconds or a minute? Yeah, the power of the Laplace transform. All right, now let's go ahead and get to our last example. I think that last integral was a little too easy, so let me throw this one at you. All right, so what do we do now? What do we do? Yes, we take it slow. We like to take things slow. Let's start by small steps, right? Don't let this problem shock you, okay? So we're going to go ahead and let's factor out the x. Let's go ahead and factor out square root of e to the x, as I notice, right? And so what we have now is we have x plus x minus 1. And then we have x, and same thing here. You can already see that this is just if we just conjugate, right? If we conjugate everything, we get x minus 1, and then plus square root of x plus square root of x minus 1. And here these two terms cancel out. So what we have is from 0 to infinity, we have 2 x square root of x square root of e to the x, right? And now this is simply equal to 2 times the Laplace of what? T square root of t? T square root of t. Do we know that Laplace transform? We know that the Laplace of square root of t is equal to root pi over 2, and it was s to the power of -3/2, right? Okay, but this one's t times root t. So what, do we turn this into an integral and use Gaussian? No. No, you don't have to do that. You do not have to do that. What we can do is use the differentiation property, if you remember, t times the function, right? So this is equal to 2 times the derivative. Ooh, be very careful. I almost forgot. Be very careful. This is negative, right? When we're doing the differentiation property, it's negative. That negative comes from the negative st in the power from the Laplace transform formula. So negative dds. Okay. Don't forget the negative. That kills a lot of opponents. Root pi over 2, and then s of -3/2. Okay, where s is equal to 1/2. So now we go ahead and compute that. This is what? -2. Let's see the derivative. Oh, well, let me take the constants out. So it would be negative root pi, right? And then here we have -3/2 of s to the power of -1. We get -5/2. So now we have 3 root pi over 2. And then s, we have 1 over, we have 1/2. So now this is what? 2 to the power of 5/2. So now 5/2 is the same thing as what? I'm too lazy. I'm just going to go like this. And then, okay, now it's easier for me to see that this is 4 root 2. So now this is equal to, I'm just going to close that. So now this answer is equal to 6 root 2 pi. And that is our answer. Okay? Woo! Alright. Well, there you go. You see how amazing and important Laplace transform is, including its properties. Super helpful. Super helpful to tackle a lot of these ugly, monstrous-looking integration bee problems. Okay, so definitely practice with these special Laplace formulas. Just, you know, as usual, just rewatch this video again and try the problems yourself. Okay, I hope that helps. Thank you so much for watching, and I'll see you guys in the next video.